P12 was the first experiment in which we had identified aluminium and also possibly silicon as species that were desirable for forming films on the surface of the palladium, which would allow one to attain and maintain periods of loading. P12, I'll briefly describe the results of. It's the first experiment in this series in ambient pressure cells in which we observed excess power. P13 was a light water replicate which went for a similar period of time. No excess power was observed. We then attempted to replicate P12 in a series of experiments, 13, 14, 15, 16, and 17, and observed excess power in each of those experiments, each of them heavy water experiments. P18 was a special experiment and in fact failed within about 80 hours of its operation. We began another series of experiments in which boron was added to the electrolyte. I'll describe P19 result because it's a special result, and the most recent experiments, C1 and C2, were experiments in which we're attempting to vary the surface to volume ratio to try and find out whether the effect that we're looking at is a surface effect or a volume effect. All of the experiments that I'm described up to C1 were performed with 3 millimeter Engelhardt palladium from a single stock, heat treated in each case in an identical fashion. Experiments that were by and large performed in an electrochemical environment that looked like this. 3 millimeter palladium cathode, either 3 or 5 centimeters long, helically wound platinum anode, 1 molar LiOD electrolyte, to which additions were made of the elements aluminium, silicon, and in some experiments boron. This is mounted inside a pressure vessel so that we can apply small overpressure of deuterium, and the pressure line connected to a pressure transducer, which is sitting above the level of the electrochemical experiment. This is the result that we obtained in P12. These are raw data and not subjected to the error analysis that we have applied the later data to. It was the first major result that we achieved in ambient pressure experiments, and one that I'm, for historical reasons, happy with. Here we observe a time when the current density was ramped through little hiccups, which were largely due to miscommunication with the technician more than anything else. The excess power for the 2 independent pairs of temperature sensors is plotted at the top. You can just distinguish, perhaps in a somewhat fuzzy presentation, the 2 different pairs of temperature sensors, but they're statistically not distinguishable. This is a period of time of 8 days from here to here, an observation of the order of 1 megajoule, representing something like 30 megajoules per mole of palladium in that observation. The first time we had achieved a result in ambient pressure cells, and the first time we had obtained a result with aluminium additions to the experiment. This time here is 1,200 hours into the experiment. Replication was attempted for a light water cell. Here I show a period of time just to show you what an observation of no excess power looks like, which is the normal condition of our experiment. We observe a period when the current is ramped to high levels. The data here show the total power observed in the experiment. This little blip here is a time when the heater was stepped up and down for calibration purposes. The excess power in this experiment sits very, very close to the baseline. The excess power is a line which fits on the baseline. The heater here is stepped up for a small period and down. P13 ran for 1,300 hours, was in thermal balance for the entire duration of that experiment. Now P13, the light water replicate of P12, was in the calorimeter at the same time as a new experiment, P14. P14, identical in all respects to P12, the heavy water cell. In this case, P12 had a surface treatment which involved helium-4 implantation. P13 had helium-4 implantation. P14, which is shown in the cell, had helium-3 implantation but was otherwise identical. Here is the same block of time. The heavy line represents the raw data for the two pairs of temperature sensors for P13, with the measurement uncertainty expressed by this light grey hatched region, showing that the excess power for P13 for this particular period of time is 0, plus or minus a small uncertainty in the energy for this period of time. And the calorimeter at the same time, electrically in series and powered from the same current source, was P14. And for the same period of time, we observe this form of excess power, 0.21 megajoules, plus or minus its assigned uncertainty, at a time in response to the current ramp shown. So here we have a case where the calorimeter was under identical conditions. The two experiments were side by side with the calorimeter being measured with the same measurement devices, and we observe excess power in a heavy water cell, but we did not observe it with the light water cell. This is a rather small observation of excess power. But the energy under this, as I showed before, as I said before, is of the order of 0.2 megajoules with its assigned uncertainty of the amount denoted. One of the important things to note in these experiments is that we, in general, don't observe excess power on the first observation, on the first attempt. This is a typical experiment, probably one that's never been performed. You calibrate the experiment with controlled heater steps at a time when the electrochemical power is low, and we will start by stepping the total power, that is stepping the heater to some high value, and then you will start to ramp the dashed line, the electrochemistry. On the first attempt, you will not see any excess power in general. On the second attempt, you may not. But when the initiation period that I described as the time has elapsed, on, for example, the third observation, as we ramp the electrochemistry at some critical current, we may begin to observe excess power in the sense that the output power determined by the calorimetric equation is larger than the input power. If you remember the equation of the calorimeter, I'm going to show you a time when, for a particular experiment, P15, a replication of P12, we ramped the current density for a particular interval of time, and the mass flow rate for the calorimetric fluid going into the calorimeter was held relatively constant. As a consequence of this current ramp, the resistance ratio for P15, which was in the calorimeter at the same time as P16, resistance ratio fell to a value of about 1.55, corresponding to a loading of about 0.96. The mass flow rate was held constant, and here we have the total power held by the computer to be essentially constant at 10 watts, and then steps to 12 watts at this time. As the electrochemistry was ramped, the product of the current and voltage increasing, the heater is shut off by the computer just to hold, the sum of the two to be constant. For this period of time, the inlet's temperature sensors, as usual, were constant, the temperature of the bath being constant, so that the inlet temperature was 35.568 plus or minus a few millidegrees for this period of time. As I described before, if the input power is constant, the mass flow rate is constant, the inlet temperature is constant, then the outlet temperatures must be constant. In this case, we observe the outlet temperatures, sensors, the two of them, sometimes they move apart a little bit, and you can see the variation. The two outlet temperature sensors were not constant for this period of time, suggesting that within the calorimetric boundary, there is a source of unaccounted for excess power. And if we calculate that from the equation, we can see this effect.